Welcome to sidza.com. Ortho-Para directing groups. In our last lesson, we learned what are Ortho-Para and the meta directing groups. So I suggest you, to go there and watch those videos. What are Ortho and the Para directing groups? Here I'm going to take certain examples of the Ortho-Para and Ortho-Para directing groups. We have learned in our last lesson that if you have any group that is having an electron pair available, right, a lone pair of electrons with that, and if you attach this group with a lone pair of electrons with the benzene ring, it can donate electrons. So therefore, due to the resonance, due to the plus resonance effect, so what's going to happen? Electrons will delocalize over the ring and you will have a negative charge at the ortho and the para positions. So therefore, electrophile, which is electron deficient, is obviously going to attack on this molecule only at the ortho and the para positions. So any group with a lone pair of electrons will be called as an ortho-para directing group, because it can delocalize, the electron pair can delocalize over the ring, and that will increase the negative charge, and the electrophile can attack at the ortho and the para positions, and you will have electrophilic aromatic substitution reactions only at the ortho and para position. So we call this group as a ortho-para directing group. Just like we have an NH2 group. NH2, when you react, when you attach it to the benzene, you see here this electron pair goes down, and this particular electron pair from the benzene ring, it will shift to this ortho position. So you get a negative charge at the ortho position. So again, you can draw one more resonating structure where you have this electron pair which is present at the ortho position. So it will be delocalized now. So you can push it down, the double bond will be formed between these two carbon atoms, and this electron pair, the pi electrons, it will shift to the para position. So now you will have a negative charge at the para position, and you will have a double bond here and here. And again, you can draw one more resonating structure. The electron pair can go down, and this electron pair will go to the ortho position. So you will have one more structure like this, a double bond here, NH2, and you have a double bond here and here, and you have a negative charge at the ortho position. So what you see here, when you attach an NH2 group to the benzene ring, the ring gets a negative charge at the ortho, para, and the ortho positions. So therefore, this is an this is ortho-para directing group. NH2 is an ortho-para directing group. Similarly, you can attach a hydroxyl group also. So all these groups with the lone pair of electrons, right, they will always release electrons over here, and that will increase the negative charge. So OH is also ortho-para directing group, correct? So amines are also, if you have an amine, NH, and you have an alkyl group over here, if you attach it to the benzene ring, again this electron pair, it will increase the negative charge. So you can say NHR, this is also a ortho-para directing group. So what you see here, all those groups with the lone pair of electrons, they can donate electrons to the ring, and that will increase the negative charge at the ortho and the para positions. So electrophile is going to attack on the ortho and the para positions. Similarly, halogens like fluorine, chlorine, bromine, all those atoms, if you attach with the benzene ring, for example, if you take a chlorine and you attach it to the benzene ring, so what you will see, electron pairs available, the lone pair of electrons on the chlorine, they will delocalize, and you will have a resonance like this. So you can see hydroxyl group, NH2 group, right, amines and halogens, all of these are ortho-para directing groups because they increase the negative charge at the ortho and the para positions. And among these different substituent groups here, NH2 and the hydroxyl group, right, nitrogen with the lone pair of electron, oxygen with the lone pair of electron, all these groups are these are called as strongly ring activators, correct? These are the strong ring activators. Halogen is ortho-para directing group, but it is a ring deactivator. So what does it mean, a ring activator and a ring deactivator? So basically, if you have a benzene ring, and you want to carry out electrophilic aromatic substitution reaction here, so if you attach a group to this benzene ring, that will suppose increase the negative charge at the ortho and the para positions, right? So suppose if I attach a group with the benzene, and now look at here, we have electron pair, and due to the plus resonance effect, you will have a negative charge over here, ortho, para and ortho positions. Now when electrophile attacks on this ring, on this benzene ring without any substitution, right? If you carry out a EAS reaction, electrophilic aromatic substitution reaction, on this benzene ring, and you carry out the same reaction, attack of the electrophile on this ring over here, right, at the ortho and the para positions, what we see, we find that the electrophilic attack will be more over here, right? It will be faster on this ring due to the negative charge, correct? Due to the negative charge, this attack will be faster. So we see that this ortho-para directing group is also a ring activator, correct? So what you can get a conclusion, we can say that ortho-para directing groups are ring activators also. So I can say like this, ortho-para directing groups are also ring activators, right? So they increase the the activity of the ring towards the electrophilic aromatic substitution reaction. So these are the ring activators. So the attack will be fast over here. And now if you attach over here a group that will withdraw electrons from the ring, okay, it's not electron donor, it is electron withdrawing. So that means it will have a negative resonance effect, right? So therefore what will happen if electrons are withdrawn from the ring? So if you attach an electron withdrawing group, this group that is providing electrons to the ring is called as electron donating group. So if you attach an electron withdrawing group, so it will withdraw the electrons here from the ring, and that will create a positive charge at the ortho and the para positions. And therefore electrophilic attack will be only at the meta positions, right? But if you compare the relative the rate of this attack of this electrophile on the ring, we find that benzene compared to this substituent group will be faster. So it will be in this particular order. So we can say that meta directing groups are actually ring deactivators, right? These are ring deactivators because they will decrease the the attack of this tendency of the attack of this electrophile on the ring. Overall you will see that the attack will be slower, correct? But halogen is an exception. You can see here the generalization that I made here, ortho-para directing groups are ring activators, except here is the exception is the halogens, right? So halogens are the exceptions here. Suppose the chlorine, it is an ortho-para directing group, but it is a ring deactivator, right? It will be a ring deactivator. Why it is the ring deactivator? It's because halogens, they have a positive resonance effect, right? Halogen atoms have a plus resonance effect, but they have a negative I effect, negative inductive effect, correct? These are ring, these are electron donors through the resonance effect, right? It is having, a halogen is having a plus resonance effect, but it has a negative I effect, inductive effect. These are electron withdrawing also through the inductive effect. And for the halogens like fluorine, the chlorine, you see that inductive effect is dominant over the resonance effect. For the halogens only, we see that inductive effect is dominant. Okay, so you can say halogens, they have a positive resonance effect, but through the negative I effect, they will withdraw electrons, and overall you see the effect is dominant from the inductive effect for the halogens. So that's why we call them as these are the ring deactivators, but moderate ring deactivators, right? In the next video we will learn what are the strong ring activators and what are the weak ring activators, right? Hope you got it. Thanks for watching the video. Bye for now.